We'll get started now real quick. I'm Jack Purdum, Whiskey 8 Tango Echo Echo. And what I want to do today is just give you an overview of what microcontrollers are and how you might interact with those. Next slide. All it is a microcontroller is nothing more than an integrated circuit chip. But the ones that most of us are going to be using are actually built on another board. Next slide. And these boards vary in cost, and you'll see that the FDIM2021 on the left is $3. And you'll notice that it has an awful lot of resources for the money, 128 kilobytes of flash memory, and that's where your program code goes, 20 kilobytes of data space, and a 72 megahertz clock. And I'll have a table later on that compares that with the ubiquitous Nano that everybody probably is already familiar with. The Teensy 40 is on the right. It costs considerably more in relative terms, but you'll notice the resource base is considerably deeper than it is for the STM family and much deeper than it is for the Nano. Okay, next. Why should I care? Well, I could say because I care, but that's not a good answer. I think that the reason that all of us should be interested in them to some degree is, next slide, because so many computers now are using them. And there's probably, if you look at any computer that, or I'm sorry, transceiver that's come out maybe in the last 3 years, I would venture to say that almost all of them are software-defined radios. If you're familiar with Hans's work, the QCX series, those are actually software-defined radios. They may not have the graphics that we see on the high price spread, but they're still software-defined radios. Okay, next slide. I can't even, if I had a nickel for every time someone's told me, I know you have to program them, but I don't know how to program, I would be able to have my little chalet in Switzerland and drink my malaria medicine at 5 o'clock every day. But I hear this all the time. I don't know how to program, and therefore I can't use a microcontroller. Next slide. I don't care. Go ahead, next slide. Before you got your ham radio license, how many of you knew, next, how to build a half-wave dipole? What a Cole-Pitts oscillator was? Did you know Morse code? Okay. If you got a ham radio license and you can still fog a mirror, you're more than smart enough to be able to program a microcontroller. And there are so many things that you can do with programming that expand your horizon. It's a new element of this hobby that is worth investigating. So how do I learn how to start programming? Next. The first thing I think you should do, and there will be people who disagree with me, I think you need to select a chip that you want to use as a learning platform. A lot of people, just say it, a lot of people prefer to use the Raspberry Pi. Some prefer the Arduino Nano, others prefer other chips. So we'll talk more about that later on in this presentation. Once you've selected the chip, then you go about selecting the tools that you can use to program that chip. And a lot of those are free for the download. So the expense is not going to be that great. Okay, next. Collect the learning resources. There are so many tutorials online about C programming and programming in the Arduino environment that you won't have any trouble collecting the resources. Next. Online videos. YouTube has all kinds of instructables on there that you can watch. And you'll see really how simple it is. Just a few simple mouse clicks and you actually can load, compile, and change a program. Next. Online books. There are a ton of these. And some of them actually are quite good. There's a course, a C course by MIT that's free for the download that is very good. Next. You can buy a real book. I happen to like this one, but I might be biased. Next. Okay, I suggest picking from this list for selecting your microcontroller. It's not exhaustive. There are a lot of other ones that you could pick, but this is what I would consider your first go at it. And also notice that the Uno is a fairly large footprint. The Nano is about the size of the first joint on your thumb. So it's quite small. And there's also one that you can buy for less than the Nano called the Pro Mini. I would not buy that. And the reason is because it does not have a USB connector on it. And the USB connector is what allows you to program from your PC and upload your program to the Nano. So I would, at least to begin with, not even consider the Pro Mini. Next. The STM32F series are inexpensive, good resource depth, and there are other things that we'll talk about that are important in making the selection. Next. The ESP32 is a very powerful chip, and a lot of people like it because it has built-in Wi-Fi and Bluetooth. So if you're interested in those particular elements of our hobby, like being able to run remotely, that might be something that you'd be very interested in. I'm not a big fan of the ESP32, and the reason is there's just too many variations of it. And there are also a bunch of pins on the ESP32 that you cannot use. And that's one reason why some of the boards will have 32 pins on it and some will have 38 pins on it. Next. The Teensy 4.0 and now there's also the 4.1 are extremely powerful microcontrollers. And they bring a lot to the table. Next. This is a pinout of the Nano. And you can see up here where this is the TX and RX signals. You do not want to use pins 0 and 1 in your programs for anything other than the serial monitor. And the reason is because that's your main communication link between your computer and the processor itself. And then most of them down here in the lower right-hand corner, most of them will use digital pin 13 to control an LED. And if you run the famous blink program, you're really controlling digital pin 13 to cause it to blink. And you can get these pinout images just by doing a search on the internet and look at the images that come up. Okay, next. This is the STM32, and this is actually the F103 series. It is very inexpensive, a lot of power, has a lot of pins. This is the one they call the blue pill. And it also has, you'll notice here that it has a serial peripheral interface pin sets. And in fact, I think there's 3 on this one. Two. And then there's also an I2C, an interconnection interface as well. And those become important when you start hanging sensors and LED displays and things like that on it. Next. This is the ESP32, and you can see up at the top in the center, that's actually the Wi-Fi and Bluetooth antenna system. The LED or the USB connectors down here, there's some support stuff. The problem is not all of these pins are available to you. This one has 30 pins brought out, and that's probably a good choice because the ones that aren't brought out, you probably shouldn't be messing around with anyway. a lot of books, including my own, detail the pins that you should stay away from. Okay, next. This is the teensy, and the teensy 4.0 is, again, not much bigger than your first joint of your thumb. But this thing has just it has a mega bunch of memory, and it has flash and SRAM. I think it's got, I think it's a half a meg of space for data and 2 megs, almost 2 megs for program space. It does not have EEPROM on it like the other ones, but Paul, who designed this board, has reserved 64 kilobytes of EEPROM that he emulates in flash memory, and it works very, very well. Okay, next. Uh-oh. Wait a minute, back up. Where's all my data? Well, that sucks. Oh, man. Let me bring this up on my system here. Okay. And see if I can. Okay. I don't know how to get this over there. Go back to the slides.
Describe it.
Yeah, I'll just describe the highlights of it. If you can put that other slide up, yeah, that one. Okay, under the resources, I have processor bits right here. The Nano, the Arduino is 8. The Teensy, all the rest of them are 32-bit processors. So that means that the data sizes are considerably larger on everything but the Nano. Flash memory, this is the second column. You get 32K with the Nano, but you get 2 megabytes with the Teensy 4. You get anywhere from 64 to 128K with the STM series, and the ESP has 1.3 megabytes. So you go from 32 with the Nano up to, well, 2 megabytes here for the, I'm sorry, for the Teensy. The next one is SRAM. And SRAM is important. The static RAM is important because that's where all of your data go. My experience is that I run out of SRAM, memory long before I run out of flash memory. And with the Nano, you only get 1 or 2K of SRAM. You get 1 megabyte with the Teensy. You get 20K with the Blue Pill, and you get 308K with the ESP series. So you go from 2 up to as high as 1 meg of SRAM between the chips. And EEPROM, you get 1K with the Nano, and you get 64K with the other ones. Those are emulated though. And finally, the last one that I'm going to go over on this table, since you can't see it, is the processor speed. The Nano is clocked at 16 megahertz. The Teensy is clocked at 600 megahertz. You can actually even overclock that if you want to, but 600 megahertz is more than fast enough for almost anything. The Blue Pill is clocked at 72 megahertz, which is about a little over 4 times faster than the Nano. And the ESP is clocked at 240 megahertz, which is, you know, almost, well, it's over 10 times faster than the Nano. So the rest of this is in the, or the rest of these tables should be in your proceedings, and you can look at that and fill in the blanks yourself. But that might influence how you choose something, because the cost of these, the Nano is $3. The Teensy is around 20. The Blue Pill is also going to be around $3, and the ESP is going to be around $10. So you have quite a choice, and your choice is going to be influenced by what you really want to do with it. Okay, next. Okay, memory. We've talked about the 2 types. Next. Flash is where your program code resides, and that includes the bootloader. And the bootloader is nothing more than a little piece of code that is smart enough to talk with your PC. So when you're programming on your PC, you need something that allows you to shove that code from your PC into the flash memory on the microcontroller. And that's what the bootloader is responsible for. Okay, next. SRAM, this is where your data resides. And to me, this is the real bottleneck. I have, well, a couple of programs written on a Nano. I ran into flash limitations, but I almost always am pushing on the SRAM limits. Next. SRAM is divided into two places called stack and heap spaces. The heap is at the bottom, and it stores all of the data that are called global and static. This includes all your functions, all of your global variables that you might have. All of that ends up in the heap space. The stack space is used for temporary variables. In other words, if you call a function and inside of that function you define some variables, they're allocated off the stack. So heap space is pretty much fixed. By the time you see anything on the screen, all of the heap space has already been dedicated. The stack space, though, is like, this is like the top of a salad plate dispenser in a restaurant. So if I call one function, it's like putting a couple of plates on the stack and it pushes it down. And if I call a function within a function, that's going to push it down some more. And if I have a lot of variables and maybe some big data arrays, that's going to push it down some more. And if I do a stupid recursive call, I can push stuff on the stack to the point where it runs into the heap space. And that's called a stack collision. If that happens, blue smoke, no, just kidding. The sad thing is that if you have a stack collision, you may or may not know about it, because this space, the heap space that's being collided with, you may have already used those variables and never use them again, and you wouldn't even know the collision happened. So the stack space, though, ebbs and flows. When I leave a function, I pop those plates off and the stack slides back up. So if I'm careful with pushing stuff onto the stack and popping it off when I'm done, and the compiler generates the code to do this for you automatically, you shouldn't have too much trouble unless you have a lot of data. Because if you have a lot of global variables, this heap space is going to grow up towards the top, and that's going to reduce your stack space. Okay, next. Clock speeds, we talked about that. Memory, flash, and SRAM, you got to look at those. The clock speed is sort of like a stoplight. The faster that thing changes, the faster you can push data through the system. So that's important for as far as the throughput of your system. Next. Pins. Most of the time you have just two pins, type of pins. Digital, and a digital pin can either be on or off. And analog. In analog depends, the values that it can assume depends on the number of bits that it uses for measuring. And the Nano, for example, uses what is a 10-bit. So you can get any value between 0 and 1023. And that can come in very, very handy for reading sensors and things like that. Whereas the digital is just on or off. You've thrown a switch or you haven't thrown a switch. Interrupt support. The Nano has two external interrupts, which means that you can hang something on the Nano, and if it gets triggered by some event, like it might be a rain detector, and if it starts raining, that will send a signal to the Nano, and the Nano will instantly quit whatever it's doing and branch to whatever routine you said should be processed when it starts raining. So an interrupt, and anybody who's raised a 2-year-old knows what an interrupt is. It's something that demands immediate attention. And The Nano only supports 2 external interrupts, but you can also use the other I/O pins for software interrupts. Okay, next. Interfaces, these are just ways of talking to the chip. I2C is interconnection and SPI is serial peripheral interface. I'm going away from I2C and I'm starting to favor SPI. And the reason is because the library support for SPI has grown exponentially over the last couple of years. Next. To give you an idea of what this means is, on the left is the 2x16 LCD display you've all seen. If you have a QCX, that's the type of display that you're using. And then you have an Arduino type of board on the other side. Actually, Hans is using the raw chip, the 328. But you can see there's a whole rat's nest of wires that have to go between the Arduino and the display, and you're chewing up those pins. And if they're used for the LCD display, you can't use them for other things. Next. Now, here's the same type of display. You're looking at the backside of it using the I2C interface. And you'll note there's 2 power wires, and then there's a clock and data line, the green and the yellow. And you've now cut the pin count from 8 down to 2. And that frees up then the other 6 to use for whatever you may wish to use. Next. The next thing that you need to consider when you choose is the IDE, which is the Integrated Development Environment. That has all the tools that you need for writing programs. It has a text editor that allows you to enter the stuff in. It also houses the compiler that allows you to convert your C code or whatever you're programming in into binary instructions that your microcontroller can understand. And it also includes something that's called a linker. And the function of a linker is to take pre-written code that are stored in libraries and stitch them into the program that you're writing. So libraries are important because you're standing on the shoulders of people who have written things and debugged them for you, which means you don't have to write it. And that's always a good thing. Forums, all of these chips that we've talked about have their own forums that you can go to on the internet and ask questions and read their answers. I belong to all forums for all of the chips that I use, and I find them invaluable for answering questions that I can't find elsewhere. Other information resources, just look on the internet for the chip that you're interested in, and chances are you'll be able to find something. Okay, next. Cost. You can buy all of the controllers on the internet from Amazon, and you can also use eBay, Microsource, Fry's, and some of the other electronics stores, Best Buy even, will carry the more popular microcontroller chips. To my knowledge, none of them carry the teensy. The best thing to do there is just to write directly to PJRC Systems and buy it directly from them. Cost is fairly inexpensive. Personally, I'm using eBay less. The Chinese now are getting very, very slow about shipping, and 2 to 3 week wait is very common for anything now that comes out of China. It didn't used to be that way, but it is now. Next. I've talked about the integrated development environment. Got a little ahead of myself. Next. The compiler. The only function of the compiler is to check the syntax and semantics of the language that you're using. Syntax are just the language rules that you have to follow. Semantic checks are to make sure they make sense in the context you used it. For example, if I say the dog meowed, that follows the correct rules for the language. There's a noun and a verb, but the syntax or the semantics are wrong. Dogs don't meow. The other thing is code generation, and that's important because the code generator is going to be different for all 4 chips. So when you download the Arduino IDE, you rightfully might be asking, well, how does it generate code for a totally different processor like the Teensy or the STM or the ESP? The reason is because when you go to use those other chips, you have to download and install what's called a software patch. And the purpose of that software patch is to add a new code generator for the IDE. So if you're going to use one of the non-Arduino microcontrollers, you need to download the associated patch. And they're very easy to find. If you look on the internet, do a Google search for installing the STM32, you'll find a bazillion entries for it. Okay, 2. Whoops, that doesn't matter, leave them up. The assembler converts the compiler output to binary files. The assemblers are really just mnemonics for the binary code that comes out and actually ends up being executed by the microcontroller. The linker, the purpose of a linker is to take those pre-written chunks of code that other people have written and stitch them into your code. And the depth of those libraries is a huge factor in how productive you can be in writing your own programs. Next. Where do you start? You know, if you got this 4-ton elephant in the room, how do you start to eat it? Well, you do it one bite at a time. And to me, any program in the world, I don't care how complicated it is or what it is, can be reduced to 5 program steps. Number 1, initialization. This sets the environment in which the program is going to run. If you're doing a database program, you're going to have to open the database and establish a link to it. If you're using a fiber optic network, you probably have to set some kind of a port for the fiber optic. All of these are initialization things that you have to do before you even show anything to the user. There are background startup tasks that you have to take care of first. Okay, next. Once you've got things ready to go and you pop something up on the screen, you're probably going to ask the user or one of those sensors or a database connection, something to input some data. And obviously you need to verify that data to make sure that it's in a form that is truly usable. Okay, next. Then you process the data and you use a plan called an algorithm to process the inputs. The whole purpose of a computer program, if you think about it, is taking input data in one form, crunching on it, and next, output it to some other form. And that processed data could go somewhere else, or you might use it in your own program. You might save it to a disk file, whatever. The steps 2, 3, and 4 just take data in one form, chew on it for a while, and spit it out in another form. Next. And then the last step is termination. And termination means more than just removing power. What you really should do is, if in the initialization step you opened a port, you should give that port back to the op system when you're done. If you opened a fiber optic connection, release the handle to it so you gracefully end the program. Now, microcontrollers are different because they are not designed to terminate. Most microcontroller programs are designed to run forever. So if you have a stoplight in a traffic pattern being run by a microcontroller, it doesn't do a whole lot of good to shut it down at 5 o'clock. It's meant to be there regardless. So termination in a microcontroller program is rare. Next. It normally only terminates when power is totally removed, or you perform a reset, and most of the microcontrollers have a reset button on them, or you had a component failure. In most of the other programs, it's designed to run forever. Next. Okay, this is a Blink program. This is probably the most, it's like Hello World in C. It's designed to make sure, well, I think it's designed to make sure that you installed the IDE correctly. And it has two functions in it. Setup, which I've highlighted in yellow, and that is the initialization step. It is setting the environment to be used for the Blink program to run. And to do that, it says, okay, I want to use LED pin 13. I want to use pin 13, and I want to use it as an output pin. If you recall, when I showed the pin out of the Nano, I said pin 13 was the LED. Well, that's exactly what we're doing here. We're telling the compiler, okay, I'm going to use the LED pin and I'm going to use it for output. Once, and that's the only setup that I'm doing here. The initialization is very simple here. Then I go down to loop, and loop is something that just runs forever. Once you get into loop, unless there's a power removal or reset or a failure, this guy runs forever. And if you look real closely, you can see the cows coming home down here at the bottom. Anyway, what we're doing here is we're doing a digital write to pin 13 and we're setting it to high. So in essence, we're turning that onboard LED on. Then we call a library routine that somebody's written for us, and we're going to delay the processor for 1,000 microseconds. So we're going to wait for a second. This L I put in, a lot of people don't put it in, but I put it in because that 1,000 is a long data type. It's not a normal int, it's a long. So I just put that in there to kind of jog someone's memory if they're reading it. After that 1 second delay, then I do a digital write to the same pin, but this time I'm going to turn that pin low. So obviously what I'm doing is I'm turning off the LED. And then I do another delay for 1 second. Once I get to the bottom here, then, because this is a loop, it goes back up to the first statement in the loop and it executes it again. So if you look at the 4 statements here, all I'm doing is turning on and off the onboard LED once a second. And that's all that the Blink program does. Okay, now, when you start to get into more complex programs, setup is going to get considerably more extensive, and loop will also get more extensive. But I think what you're going to find is buried in loop will be calls to input the data, step 2. You'll have calls to process the data, step 3. And then you'll have calls to output the data, step 4. And then you repeat it again. So we don't hit that termination step. We just continue to spin around in here. Okay, next. Oh, crap. I had 2 more slides. Let me go down to the bottom here and see if I've got them on this. It doesn't look like this has it either. I don't think I gave the latest to Al. But anyway, all it is was a summary. And I was trying to point out that the cost of getting started in doing something with a microcontroller is probably under $5. If you go out and buy a Nano and have a USB cable that can run from your PC to the Nano, it uses the voltage from the USB connector, so you don't even have to buy a power supply. And that would be enough to get started. And once you get started, I've got you, because you'll find that this is a whole new avenue in your hobby that I think affords you a lot of different options in terms of things that you want to do. And you can do them in software rather than hardware, which is the big advantage of software-defined radios. It's very easy to change filters, to change other elements of the radio without having to change a hardware circuit. Okay, I finished 5 minutes early.
Hey, thanks,
Any-
Jack.
Any questions?